Apache Kafka is the backbone of real-time data streaming for many companies. To tackle storage challenges, Apache Kafka introduced tiered storage as part of KIP 405. But here is a question. Does tiered storage slow down Kafka? In this video, we will break it down step by step. Understanding Kafka's zero copy mechanism, how tiered storage works, and whether it affects performance using Uber's real-world implementation. Hi there, welcome to Tech and Career Bytes. I'm a software professional with over 2 decades of experience, including 7 years in leadership roles at a global product-based organization. Kafka traditionally retains all its data on broker nodes. That works fine until you need to retain the data for longer periods. As data piles up, brokers struggle with a few challenges. More storage means adding broker nodes even when CPU and memory are not the bottleneck. This tight coupling makes independent storage scaling difficult. Larger clusters mean higher deployment and maintenance efforts. Scaling storage traditionally meant scaling compute, which is not cost effective. Clearly, there is a need for a better approach. Enter tiered storage. Tiered storage solves this problem by decoupling storage from compute. Here is how this works. Hot data or recent messages stays on broker nodes for fast access. Cold data or older messages are moved to remote storage like Amazon S3, Google Cloud Storage, or Azure Blob Storage. This reduces a broker load and lets you scale storage independently without impacting broker performance. But why did Uber need this? Let's find out. Uber deals with massive real-time data streams. Their Kafka clusters handle petabytes of data, making storage efficiency critical. Here is what they wanted to achieve with tiered storage. Scale storage without affecting broker performance. Offload older data to cloud-based storage. Keep hot data in brokers for fast access while archiving older data efficiently. Reduce storage load on brokers, cutting costs and improving recovery speed. Their main goal? Extend Kafka's data retention without increasing cluster size. Uber designed a two-tiered storage approach. Local tier stores recent data for a few hours, ensuring low latency consumption. Remote tier holds few days to few months older data for applications needing historical data. Tiered storage is seamless to implement. No modifications needed for existing Kafka clients. Everything just works. Let's now look at how they implemented it in Kafka. To make this work, Uber fine-tuned Kafka's storage settings. Uber configured Kafka to balance between fast local storage for real-time processing and cost-efficient remote storage for long-term retention. These settings ensured fast access to recent data while maintaining affordable scalable storage. Shown here are the sample configurations. But there is a catch. Tiered storage impacts Kafka's performance in one key area. A major concern with tiered storage is its effect on sendFile API, which powers zero copy data transfer. Why does this matter? Let's dig deeper. Sendfile bypasses user space memory, allowing Kafka to send data directly from disk to consumers. This speeds up data transfer and minimizes CPU overhead. But tiered storage changes this. Let's see how. One of Kafka's biggest strengths is zero copy data transfer, which drastically reduces memory usage and system calls. Here is how Kafka does it. Instead of copying data multiple times between memory and disk, Kafka directly transfers file bytes to a remote socket using the sendFile API. This simple optimization allows Kafka to maximize network throughput. The typical data transfer path from a file to a network socket involves multiple steps. First, the operating system retrieves the data from the disk and stores it in the kernel's page cache. The application then reads the data from kernel space into a user space buffer. Next, the application then writes the data back to kernel space, this time into a socket buffer. And finally, the operating system copies the data from the socket buffer to the network interface card buffer for transmission over the network. This process involves 4 data copies and 2 system calls, making it inefficient. However, sendFile mechanism eliminates redundant copying. With sendFile API, the OS can directly transmit data from the page cache to the network, bypassing intermediate copies. In this optimized path, only the final step, that is, copying to the network interface card buffer, is necessary, significantly improving efficiency. With zero copy optimization, data is copied into page cache just once and reused for each consumer instead of being repeatedly transferred between memory and user space. This allows messages to be consumed at a speed approaching the network's maximum throughput. In a Kafka cluster where consumers have already consumed most of the available data and are in sync with the new messages, there is no need to read data from disk. Since the data remains available in memory, that is page cache, Kafka can serve it directly, ensuring fast and efficient access without disk reads. This also eliminates the need for additional caching techniques to speed up data retrieval. But how does the tied storage affect this? Without tied storage, Kafka's data transfer path is super efficient. Operating system reads data from disk and stores it in page cache. After this, Kafka sends it directly to consumers using sendFile API. Only one copy of the data is in memory, leading to faster consumption. However, with tied storage, things are different. Cold data needs to be fetched from remote storage before serving consumers. sendFile API can't be used, leading to extra memory copies and increased latency. Does this mean tied storage slows Kafka down? Not necessarily. Uber implemented smart optimizations to minimize the impact of tied storage. Frequently accessed cold data is prefetched and cached in brokers. Smarter retention policies implemented that dynamically adjusts hot-cold tier cutoffs based on real-time access patterns. Remote data is retrieved in batches for efficiency. Historical data is served via a different path, preventing real-time consumers from experiencing delays. Additionally, Kafka brokers stream remote data into an in-memory buffer before sending it to consumers. This approach ensures that network threads remain unblocked, preventing performance bottlenecks. This ensures that real-time workloads primarily hit the local tier, preserving Kafka's high performance. By implementing tied storage, Uber achieved these benefits. Scalable storage without increasing broker count. Faster recovery by reducing broker-to-broker data movement. Easier cluster rebalancing and reduced downtime. And cost-effective storage using cloud-based solutions. In short, Uber improved Kafka's scalability while keeping costs low. Kafka's tied storage is a game changer for companies dealing with massive data streams. Uber's implementation proves that smart storage strategies can improve scalability, cut costs, and maintain performance despite storage offloading. As Kafka continues evolving, tiered storage is set to become a standard feature for large-scale data streaming. If you found this video helpful, give us a thumbs up and subscribe to our channel for more interesting tech topics. Do check out our other videos on software performance optimization case studies, coding, system design, big data, and career growth. My name is Rupa, and I thank you so much for watching this video. See you next time.